Hello everyone, in this video, I'm going to show to you how to derive the mean, the variance, and the moment generative function for the gamma distribution with a probability density function shown here. Function of x given the parameters alpha, beta is equal to 1 over gamma of alpha, beta raised to alpha, x raised to alpha minus 1, e raised to negative x over beta, where this probability density function is defined from x equals 0 to infinity, and both the parameters alpha and beta are greater than 0. This gamma of alpha is defined to be integral of this one. And we have here one of the identities of the gamma function, which is gamma of alpha plus 1 equals to alpha times gamma of alpha. If you are still unclear about this identity, I have provided a video that shows how to derive this identity. So I have provided the link in the description below, so you can check it out. Let's now derive the mean. Mean is equal to expectation of x, and expectation of x is the integral of x times the probability density function, which is this one, 1 over gamma of alpha, beta raised to alpha, x raised to alpha minus 1, e raised to negative x over beta. We have dx. This is from 0 to infinity, so we'll have 0 to infinity. Now, we can move out the constant from the integration. We'll have 1 over gamma of alpha, beta raised to alpha. Then we'll have integral of, for x, we can combine them. So we'll have alpha minus 1 plus 1 is alpha. So x raised to alpha. Then we have e raised to negative x over beta. Then we have dx from 0 to infinity. Now, we're gonna simplify this integral using this definition of gamma function, so we can remove the integral and replace it with an expression containing a gamma function. So let's do that. If we try to compare both sides, or say both equations, we have here t, and this one is x over beta. So let's do a transformation. Let t is equal to x over beta. Then if we do that, x will become beta times t. Then dx is equal to beta dt. Then mean is equal to, so we have these constants, 1 over gamma of alpha, beta raised to alpha. Then we have integral of, for x, we're going to use this one, beta t raised to alpha. Then we have here e raised to negative, for x over beta, we have here x over beta, we have t. And dx is this one, beta times dt. This is from, if x equals 0, then t is 0. And if x is infinity, we'll have t is infinity. It's okay to do that since this one is 1 to 1. We will have no problem with the transformation. Then let's move out the constants from this integration. So the original constant is this one. Then we have here beta raised to alpha. Then we have here beta. Then we have the remaining is t raised to alpha. Then e raised to negative t dt from 0 to infinity. Now this beta raised to alpha can be cancelled because they are both in the numerator and denominator. Now we'll try to compare this one to this one. This one is same, but here they are not same. And we have here alpha and here alpha minus 1. We're gonna use another variable. Let alpha is equal to another variable delta minus 1. Then we'll get mean is equal to 1 over, let us retain alpha in here. Then we have still the beta at the top. And we have here integral of t raised to delta minus 1. We have here e raised to negative t dt 0 to infinity. Now if we try to compare this one and the definition of our gamma function, they are the same except that this is delta and this is alpha. So this one is equal to gamma of delta. Now, since we have here delta, delta is alpha plus 1. So this one is gamma of alpha plus 1. So we'll have mean is equal to beta times gamma of alpha plus 1 over gamma of alpha. Now, we can use now this recursive identities. So let me rewrite it in here. Gamma of alpha plus 1 is equal to alpha times gamma of alpha. Then gamma of alpha plus 1 over gamma of alpha is equal to alpha. So we can use this one for this one. So we have beta alpha, or we can rearrange that as alpha beta. That's our mean for this gamma distribution. Let's now derive the variance. Variance, originally it has a formula expectation of the square of x minus expectation of x. And we have also another formula which is expectation of x squared minus square of expectation of x. We're gonna use this one. For expectation of x, we have the mean which is equal to expectation of x equal to alpha beta. So we're just gonna square this alpha beta for this term. For expectation of x squared, we need to derive it first before we derive the variance. So let's derive the expectation of x squared. This is equal to integral of x squared times the probability density function, which is this one. Dx. This is from 0 to infinity, so we'll have 0 to infinity. Now let's move out this constant from the integration. We have x raised to alpha minus 1 plus 2 is alpha plus 1. Then we have the rest of the term from 0 to infinity. So in this case, we're gonna do the same what we have done for the mean, which is to remove this integral. We're gonna try to make a transformation that will make this one similar to this one, so that we can remove the integral and we have the expression that contains a gamma function term. So let us do a transformation now. Let t is equal to x over beta. If we do that, x will become beta t, and tx is equal to beta dt. Then expectation of x squared is equal to 1 over gamma of alpha beta raised to alpha. Then integral of, for x, we're gonna use beta t, and then raised to alpha plus 1. Then e raised to, for x over beta, we have t, so negative t. Dx, we're gonna use this one, beta dt. This is when x equals 0, t is 0, and when x is infinity, t is infinity also. This one is 1 to 1, so we should have no problem with that transformation. Now, let's move out the constant from the integration. So original constant is, then this is beta raised to alpha plus 1, and we have here beta. Then we have integral for the remaining term, t raised to alpha plus 1, e raised to negative t dt. This is from 0 to infinity. Now for this one, beta raised to alpha plus 1, so alpha plus 1 plus 1, which is equal to alpha plus 2, then minus alpha is 2, so we'll have beta raised to 2. Let's rewrite it in here. Beta raised to 2 over gamma of alpha. Then we have integral of t raised to alpha plus 1, e raised to negative t dt, 0 to infinity. Now, to make this one similar to this one, we have alpha minus 1 here, and this one is alpha plus 1. I will use different method that is different from what we have done for the mean. Let us first rewrite this definition. Yeah, so this one same. Now let us have gamma of alpha plus 2 will have integral of t raised to, for alpha, we're gonna use alpha plus 2 instead. Then we have e raised to negative t dt from 0 to infinity. This one, alpha plus 2 minus 1 is alpha plus 1. So we'll have equal to integral of t raised to alpha plus 1 e raised to negative t dt from 0 to infinity. Now this one is same with this one, so we'll have here, instead of this one, we will use gamma of alpha plus 2. So we'll have beta squared gamma of alpha plus 2 over gamma of alpha. Now we're gonna use the our identity for this one. So we'll have gamma, I will rewrite it in here. Gamma of alpha plus 1 is equal to alpha times gamma of alpha. We then have gamma of alpha plus 2. Similar to this one, this alpha is based from alpha plus 1 minus 1. So in here we have alpha plus 2 minus 1 is alpha plus 1. Then also this is alpha plus 1, similar to that above. Now for gamma of alpha plus 1, we're gonna use this one instead because it is equal to gamma of alpha plus 1. So we get gamma of alpha plus 2 is equal to alpha plus 1. Then this one, gamma alpha times gamma of alpha. So we have gamma of alpha plus 2 over gamma of alpha equal to alpha times alpha plus 1. So we're gonna use this one instead of this one. So we'll get beta squared times alpha plus 1 for our expectation of x squared. Now for our variance, we're gonna rewrite the formula, this one in here. So we'll have expectation of x squared minus the square of expectation of x. For expectation of x squared, we're gonna use this one, beta squared alpha times alpha plus 1 minus, for square of expectation of x, we're gonna use the square of this one, alpha beta. So we'll get square of alpha beta. Then we'll have, let's distribute this one, beta squared alpha times alpha is alpha squared beta squared. Beta squared alpha times 1 is alpha beta squared minus this one is alpha squared beta squared, and we have here alpha squared beta squared and minus alpha beta squared, which is equal to 0. So the remaining is alpha beta squared. That is our variance. Let's now derive the moment generating function for the gamma distribution. The formula for the moment generating function is expectation of e raised to tx, and expectation of e raised to tx is the integral of e raised to tx times the probability density function, which is this one, dx. This is from 0 to infinity, so we'll have 0 to infinity. Now we can move out the constant from the integration. Let's do it now. Then integral of this is x raised to alpha minus 1. Then we can collect exponentials here. So we'll get e raised to negative 1 over beta for this one minus t in here, because minus t and minus will have plus, then we'll have x. Then we have dx from 0 to infinity. Similar to our derivation of mean and variance, I want to make this term here to be similar to this one. But if you compare this one, here t is a constant, while here t is a variable. So it is safe to change this one to another variable, let's say into y. This is safe so that we'll not be confused between t in here, which is constant, and here y as a variable. Now let's do a transformation to make this one similar to that, so that we can remove this integral and make an expression with a gamma function. Let y is equal to, so y here equal to this one. So we have x. Then if we do that, x will become y over 1 over beta minus t. Let's simplify this complex fraction. We get y over, let us multiply beta with each term. We'll get 1 minus beta t over beta, or this one will become equal to beta over 1 minus beta t, y. Then dx is equal to, the only variable in here is y, so we'll get beta over 1 minus beta t dy. Now let's do the transformation. Let me move this one a little bit. Our moment generating function is this constant. Then we'll have integral of, for x, we're gonna use this one. Raised to alpha minus 1. And we have e raised to negative. For this one, we're gonna use y. And dx, we're gonna use this one. If x equals to 0, this y will become 0. And if x is infinity, y will become infinity. Then let's move out the constants from this integration. For the constant in here, let us move it now. Then for the constant in here, let me write it in here. Then we have integral of what are the variables left. We have y raised to alpha minus 1, and then e raised to negative y dy. This is from 0 to infinity. Now this one are same. So we have alpha minus 1 plus 1 is alpha. So we can cancel out minus 1 and also this whole term. So the remaining is alpha. So we can rewrite it in here. Let me distribute alpha between numerator and denominator. So we'll get first our original constant, then beta raised to alpha over 1 minus beta t raised to alpha. Actually, this beta raised to alpha are cancelled, so we get here, if we compare this one in here, they are the same, so we can change this one into gamma of alpha. This is gamma of alpha, so we'll get gamma of alpha. But gamma of alpha is in here and here, we can cancel them out. So we're left with 1 over 1 minus beta t. This is alpha, which is our moment generating function.